Hello. In this lecture, I will cover chapter 2 of the mathematical economics course. Chapter 2 deals with production and cost function. In this particular video, I will only cover the production function. So the concept of production function. The production function represents the relationship between input and output, and we talked about that earlier. The output, let's say to simplify corn, the production of corn is a function of a lot of variables. That includes weather, right, fertilizer, etc., rain, and so on and so on. So, and those all those variables are represented by the axis here. So depending of the complexity of the model, we can have 20 variables or sometimes more that are function of the output. That means that different quantity or level of those inputs determines how much yield of corn will be produced, or for cow, how much milk will be produced by a cow. And so if you're thinking about the milk production per cow, for example, you can include the variable music, or you can include the variable where the cow is going to rest. I think some research have shown that cows are more productive when they rest in the very clean area. I think they put beach sand for cow to rest on instead of elsewhere, and they're more productive. So typically, given that we have a two-dimensional graph, okay, that we're dealing with, to simplify, we are going to make y vary as a function of only one input. Okay, so here we have one input that varies, and here we have all those input that varies. And this is not our model. The model we are dealing with here is this one here. Okay, so when we have one output and one input. The question of obtaining the data to define the production function. Typically, but that's kind of the old method you would use, is still available. Most reliable way to obtain the data is to design experimental plots. And for cow production, for example, will be the same thing. You are going to divide the cow into multi-different groups and subject them to different variable exposure, right? So one cow will sit and rest on beach sand, and the other cow will rest well, maybe the entire populations in sometimes the poop. So those are the type of experiments. For grain, the experiment will be multiple plants, multiple subfields, okay, experimental area where they are all sharing the same soil, and given that soil, they are all subject to the same weather, rain, etc. And given all that, you can vary either the amount of pesticide that is applied, the amount of fertilizer, etc. But you can vary only one variables. You can change one variable at a time to see how that variables isolated affect the output as a whole. However, more and more, I personally use productions of growth models for my dissertation. That means that I model, right, the growth of a crop. I model corn and soybean, and I can subject that growth to different variables. And those variables are collected in the field. So, for example, when I went to model the production of corn in Africa, I collected rain and weather data for the past 30 to 40 years. So that data will be input into a model and will give me the actual, quantity of rain and how weather affects yields in those areas, given that in Africa, typically most crops are rain-fed crops. So we have different types of production functions, and the most well-known production functions is the Crop-Douglas and the Spearman production functions. So what I did here is I collected the data from the textbook, okay, and I derived the function from that data. So I'm going to show you here how that was done. So I use the equation 2.1 that is proposed in the textbook on page 30, and that equation is y equals x squared minus 1 over 30 x to the power 3. And so that's what you see here, okay? So in Excel, if you want to write these equations, it's going to be, so the cells A, and so A4, okay? And I bring that to the power square. That's how you write square in Excel. I put that in parentheses, and I subtract 1 over 30 time, again, the same data. So this is A. So here, times, so this is times, maybe I'll write this, times A4 to the power 3. And so basically, y equals 2 square minus 1 divided by 30 times 2 to the power 3. And that will give me 3.7. Okay, so now you can see how I get this, those data, and then I copy it. And so to show you in more detail how it's done, I'm going to delete this. And so bear with me and do the same thing, or take notes about how to do it by your own, because I may ask you to do that on an exam or homework. So it's x. Okay, so equals to A4 to the power 2, close parenthesis, minus open parenthesis, open new parenthesis to make it easier, 1 divided by 30, close parenthesis, times, I have to put the time, A4 to the power 3, and I close the 2 parentheses, and then I enter. Okay. When I've done that, I just go to my B4 cell and I drag it as far as I want. Okay, so that's what gives me those results here. I didn't know that we will copy. And so you do the same thing for average physical product and marginal physical product. So for marginal physical product, of course, is going to be the difference in y divided by the difference in A, right? So marginal physical products equals change in Y divided by change in X. And so with Excel here is going to be, let's say, B4 minus B3 in my example, divided by A4 minus A3, and just keep on doing that. And so that's what we got here, okay? And so to get this production function that I have here, I'm going to delete this one. I cannot make all the changes I want here. Okay. And I'm going to insert. And so here, well, is a scatter, right? Because you have X and Y. And so, oops, I need to select my function first. So I select this, and then I go to scatter with line because I want lines, and that's what I got here, right? That's my production function, okay? It's that easy, right? It's that simple. And you can do the same thing, then you do the same thing for the other one, okay? And so here, you are going to select X, then you press the control, you hold control, okay, to select exactly what you want, and you insert that, right? So, but notice what I did here, okay, I didn't go all the way down to minus 40, I cut it, and to cut that, I just go here, and I limit my minimum to minus 15 because I just don't want to see all that. And so that's how I cut back the Y section. So this is how you can graph, okay, a production function. And so now let's go back to PowerPoint. Okay, so that's how I get this function, okay. And so what are the assumptions related to the production function? We already talked about the perfect competition environment, okay, both for the input and the output. That means that producer only have access to the market price. They don't decide on their own price. And so we also assume, as earlier, that all but one variable is constant. They cannot vary, right? We assume that they're the same, and they include all these soil, etc. Management practices too, okay, and prices. And they also all have the same level of uncertainty or certainty. So typically, we model uncertainty by using stochastic variable. That means variable that can change randomly. And so we include a random functions in the model, okay? And so I use, for example, stochastic variable for weather, and also for output price, because in the real world, the price vary, right? And so we can make those variable also change, but that is the larger economic model or econometrics model. The level technology, okay, you assume not to change either, to be of the same constant over time, and we call that the state of art. The length of period of time, okay, that is important too, because in the short run, and this refers to your macroeconomic classes, we can assume that land and maybe equipment, some type of equipment are fixed because you cannot change them over time, overnight. And in the short run, you can only change, all the different input except for land, etc. But in the long run, everything can change. So gets to a classical production function, we have three basic decision problems. First, what combination of products should we be producing. Okay, and typically farmers produce different types of products: corn and soybean, winter wheat, and cotton, etc., etc. At what level of output should each be produced? And those are the hard questions that farmers need to answer. And this is what this class help you understand, at least theoretically. What combination of input should be used to produce each product or each output? And so the objectives I will talk about earlier is profit maximizations. And so we assume that it's not always the case, but we assume that. Where resources are limiting, solving each problem must relate to the other problems. So each problem is not independent, but we try to make it independent by keeping all the variables fixed. So here, okay, see, this is the slope of the production functions at point D. The stages of productions, and I will come back to that. Okay, we have a sections of increasing return, decreasing return, okay, and negative returns. And so virtually all production functions follow this arrow here, okay, follow this type of curve. Of course, this is, relation between input and output. As discussed earlier too, the function is homogeneous. Okay. So I just showed you earlier how I obtained those data here, and also how I get the average physical product and the marginal physical product. So the average physical product is the slope of a particular straight line that passes through the origin. And so here, for example, right, the average physical product is the slope from the origin passing here. And this is over here, we have two levels of average physical products given where the curve stands. And so what we are typically looking for is this one here, right? The maximum and the minimum's average physical product. So average physical product increases, which move counterclockwise, okay? Sorry, average physical product increases as we go in this direction here. Marginal physical products measures the amount that total output increases or decreases as input increases. Okay. And so that's the marginal, is as we increase input from 5 to 10, we're going to measure about how much output increases, right? And so those are, so changing increase over changing outcrease, that is the marginal physical product. And the marginal physical product is actually the real slope of the production function, okay? And so I'm getting back to you. So how do we compute those physical products? So given our earlier equations, okay, and our earlier equation was y equals x squared minus 130 x to the power 3. And so if I take the derivative of that, this is what I get here, right? So it's of course 2x, come here. 2x minus 3x squared divided by 30. And so if I put, I have 3 here and 30 here. So I simplify, right? So I got 1 and 10. So that is my marginal physical product. So you see that this curve that I have earlier here, right? Okay, this curve, I call it A, this point A, is both the slope of a production function, and we saw that is the marginal physical product, but is also the average physical product at point A. They cross there, they become the same thing. And so when they become the same thing, and I say they cross, okay, we can graph them here, right? So at this point here, A, average physical product and marginal physical product are the same. And so if they're the same, so they have the same slope, okay? But those are different slope of the average physical product at different points. Now, the inflection point, okay, is important. As I showed earlier, output increases as an increasing rate. That means that for the same quantity, for a given quantity of input added, output increases even more than what was added, right? And so, let's see. And you can see that here, when I compute the marginal physical product, okay? So the marginal physical product increases to a point, and that will be the inflection point, right? So here the marginal physical product is increasing at an increasing rate, then it increases at a decreasing rate, and then it becomes negative, right? And so that's how we are going to determine the different stages. And so, or to a point where average physical, marginal physical products increases at points at the increasing rate and start increasing at the decreasing rate, we have the end of the first stage. Okay, so the first stage starts at the inflection point. Okay, when average marginal physical product is at the maximum. So over here, the average physical, the stage one, we start with the inflection points and go to the point where we have the point where APP equals MPP. And there we have an increasing, right? Increasing, what you guys should read earlier. And then we have, let's see, in our example, right? So in our example here, stage one is going to be the top of marginal physical product. So our stage one start here and it ends here. And our stage two was 0 here and here. So basically at the maximum, okay, that's the height we can go, stage two and stage three. And so you definitely don't want to stop producing at stage one, so you can continue to produce. And you also don't want to stop producing at the beginning of stage two. You want to continue until you can get the maximum possible output. Past this stage, you are here, okay, around 20.5. Past this stage, the marginal physical product says that if you increase your input from 20 to 20.5, your output is going to decrease from 133.3 to 133.1. Right? So why do you ever want to be in positions to spend more in input, but the reward will be a lower output, right? You spend more inputs, and by doing that, you reduces your production. This is obviously not smart, and no one, no producer in his right mind want to be in that stage. So those are the implications here. And so again, the margin, the MPP curve is at its maximum at the inflation point. Okay, so that's why we call it here, right, at the inflation point. And so in our graph is here. So our inflation point will be around between 10 and 12, okay, when the MPP is at its maximum. After that, it starts decreasing, right? So it increases at an increasing rate all the way to this maximum, then is increased at a decreasing rate from 10 to a little bit past 15, and that is our limit of our stage 1. Then you want to continue producing until you shouldn't stop producing. And so this is where you stop. And so in this case, you should not be adding more input because that's the end. And so this is logical. So why is it that marginal physical products increase as an increase, sorry, total output increases as an increasing rate? Because the marginal physical product is increasing. It's that simple, right? When marginal physical decreases, okay, until you come to 0, okay, by adding input, you are getting less, but you are still less output, but you are still getting more than 0, right? And so anytime you add input and it gives you input and gives you more output than before, then you want to continue adding input because you still have some, some additional return. At the end, the question will be, what are the costs of those additional return? Okay, the product and the price of the output and the price of the inputs. That's something else that we will be discussing later. So those are the different stages that I talked about to you earlier, and we talked about the law of diminishing return. And to the law of diminishing return, that's what I just explained, right? Is when marginal physical product starts to decline instead of increasing, right? And that stage 2, you still want to continue producing. And so I'll let you read, the different description that I gave of each stage. Now, as I showed you earlier, right, we can, well, you see to our equation is y equals x squared minus 130 x to the power 3, okay? And so this is obviously the algebraic or mathematical description of this function here. And from there, we can derive the marginal physical product, as I talked about earlier, and the average physical product. So we want to have the average marginal physical products, okay? We want to see what that number is. And to know what that number is, right, what we do is we set up the slope to 0. Why we slope to 0? Because when we talk about our output, okay, our total physical product, when you get to optimum here, okay, the slope is 0, and that we discussed that in our previous lectures. Slope here equals 0. And so, and that is marginal physical product. See, the marginal physical product is the basically slope of the production functions at different points. At the maximum here, we want to know what is this value, okay? In our example earlier, I think the value was the maximum here, the value was somewhere around 20, okay? Between 20 and 21, okay, just about here. And that's why here actually in this example, I decompose. So say every time I increase by 2, but when I increase by 2 from 20 to 22, okay, I jump suddenly from 187 to minus 213. I say, well, there got to be something in the middle. So let me get as close as possible Let me get as close as possible to the actually optimum value here. Okay, that's why I went from 18 to 20, 20.51, 20, etc. to 21. So, and that it shows on the curve here. And so that's how we did this, okay? And we set it to 0. And when we set it to 0, we derive x. So that's what I done here. And we found that x equals 20. So here's 20 on my graph is a little bit over 20, but roughly it's 20. We also try to find out what's the inflection point. Where is the inflection point, right? And the inflection point is where, so the inflection point, okay, is where inflection point, right, is where the stage 2 is where the average physical product equals the marginal physical product, right? And that's inflection point. It's where, so the average physical product is at its maximum over here. I'm drawing, right? And so we are going to set up the slope of the average, um, um, the slope of the average physical product to be equal to 0. And so first we obtain the average physical product, okay? And then we set that slope to be equal to 0. So what is the average physical product? So average physical product equals x squared minus 1 over 30 x to the power 3, right? Divided by x. Okay, so the average physical product is going to be x minus 130 x square. And so we set this to equal to 0. Okay, so that is average physical product. And when to set it to equal to 0, we have to draw x. And so I can show that another time, but we'll find that x is equal to 15. Okay, but basically this is the function that we set to equal to 0 for the average physical product. So finally, the elasticity of productions and point of diminishing return. So elasticity, that's back to your principal class, elasticity of production or production functions is the concept that measures the degree of responsiveness between y and x. So see, to find the optimum, right, we don't know if we should look at the optimum of the average production functions, the MPP, or the production function itself. And so we use the elasticity to see, well, okay, what should be the best. And so if we want to look at the elasticity of the functions with respect to x, right, there's a formula there. And if you derive that, we'll see that, so I reproduce this formula over here. And so that is this, right? Changing y divided by y, x divided by x. And if you rearrange this, you know that when I have this is equal changing y, x, y changing in x, okay? And we can easily break this down by rearranging it. And so we just take rearranging, okay? Rearrange. And so we separate the two, and we can see that this is the marginal physical product, and this is the inverse of the average physical product, because average physical product equals y divided by x, and so the inverse is going to be x divided by y, okay? Inverse average physical product, okay? And that's what we have here. And so that is 1 divided by average physical product. This is not really clean. So average physical product equals y divided by x, and inverse equals 1 divided by average physical product, which is equal to x divided by y. Okay. And so at the end, elasticity is marginal physical product divided by average physical product. So I'll solve it for you here, right? And you can go, you can see how I did that. So basically, I multiply, this is 30, okay? So I multiply the numerator and the denominator by the same number, 30. And so that gives you all this result here, okay? And so that is the elasticity there, okay? So I have this here too. And so from there, once we have a function of elasticity, right, we can plug it in. So we take the different value of x, okay, because the elasticity, the function, elasticity functions is function of x, right? And so what we do is just, again, we put the x in this function there, given that, take this function, okay, this function here, and replace by x. And that will give you us the elasticity. So in particle term, if I go back to my Excel, I think I did it there, is here, right? Okay. This looks a little bit complicated, but I'll change the color for this. Oops. Okay. So the function I have here, elasticity. So our x is 825, cell 825, okay? And so what I do, I just apply my function. And so the elasticity of P equals, if I can remember this, function of elasticity of P that we found is 60x minus 3x squared divided by 30x divided by x squared, okay. And I just need to get back to my Excel. Okay, so true. I don't know how to remove this now, but 60x minus x squared divided by, I need to have a better memory. Okay, so the elasticity is 20x minus x squared, and this is the same as 60x minus 3x squared. Okay, so I simplified. And so that's the function I have there then. Okay, just anywhere there. And so when x equals 10, so I have 20 times 10, and that is what I have here. Okay, 826 is 20. Oh, here I used 60. Okay, times 60 minus, so I use 60 in my example. I use 3 here. Okay, so I use 60. I don't know why. I should have simplified. So A, that is 20. So my example is 60. So 60 times 8 and 826, which is 10, okay, minus 3 times 10 square, right? 10 square is 826 square divided by 826 again, okay? Divided by 10 times, this is, should be 30. 10 times 30 minus 10 square. And that's what will give me that equals to 1.5. Okay. So when x is equal to 10, okay, elasticity of products is 1.5. That means when I increase x by 1, okay, when I increase x by 1, output increases by 1.5. And so from here, that's where I know that I'm in over here in increasing return, right? And increasing return, because as I add input, I get more output, right? When x equals 15, I get 1. Elasticity equals 1, okay? So when x equals 15, elasticity of production equals 1. That means what? That means that when I increase input by 1 unit, I get 1 unit of output back. Okay, this is great. However, if I get to 18, in my example here, when x equals 18, then elasticity becomes 0.5. That means, so when x equals 18, elasticity equals 0.5. That means that when I increase my input by 1 unit, I get only half back in output. So I don't want to be there, and this is stage 3, okay? And as we know that, this is stage 3 when output start decreasing as I'm increasing input, and you can see it through computations of elasticity in our example, okay? Okay, so that should be about it for this problem. So everything that is here, that's what I showed you earlier. And so the next lecture, we'll talk about the cost function. Okay. Okay, thank you and see you next time.